Hello, everyone. So, we're going to continue our conversation on electrochemistry today by focusing in on the half reactions. So, we've already gotten a little bit of information about what a whole electrochemical cell can tell you, but a lot of times we're going to want to use those electrochemical cell potentials and use them to give us some information about individual half reactions. So, let's go ahead and go back to our good old friend, the lead acid battery, and focus in on just one of the reactions. So let's go ahead and focus in on the reduction reaction here of lead oxide reducing to lead sulfate. So if I want to essentially determine how favorable this reaction is, I might want to go ahead and figure out the potential of the system. But we run into one major problem, which is this poor little electron, which is stuck on our lead oxide electrode. It needs to go somewhere. And so, what I need to do is try and figure out how much energy that electron has. But here's where the whole idea of reference state becomes very important. Because if I'm essentially reducing the system, that electron needs to go somewhere. So, I need to have a set reference energy of how much potential the electron will have if it goes to a given location. So there's multiple different reference states we can use. However, the single most common is a hydrogen electrode. So this is often known as the standard hydrogen electrode. And the idea here is I'm going to combine my little electron, which is going to be placed on a platinum electrode, and then go ahead and combine it with a free proton in solution, and this will make hydrogen gas. So because I'm going to typically be using this as an electron source, I should be more specifically thinking of the oxidation reaction. So what I'll do is I'll go ahead and I'll feed in hydrogen at 1 atm. I'm going to go ahead and combine it with an electron on it will go ahead and place an electron on my platinum electrode, which can then go off to go do what it will on my cathode. And this will leave behind essentially one little solitary proton. But as we've seen before, concentration matters when I'm talking about potential. So we're going to say that this proton exists at a 1 molar, or more specifically, 1 normal state. So essentially, whatever proton concentration is represented by a 1 normal solution. And this is essentially referred to as the normal hydrogen electrode if I'm dealing with a 1 normal solution, or a standard hydrogen electrode if I treat a system of 1 molar protons as if they were ideal. Functionally, these two numbers should be the exact same. And again, this can be given in line notation as a platinum electrode, 1 atmospheric hydrogen, and 1 normal protons. And this is going to be my classic state for an oxidation, for my oxidation reaction, which I'm comparing all my reduction reactions to. Now, it is worth noting that since it is an oxidation reaction and I have given you the potential as the reduction reaction, we should think about what the oxidation reaction potential is, which would also be 0, because all I need to do is flip the sign on my potential to get the flipped reaction. So this is also one of the nice things when considering the standard hydrogen electrode, is it has a 0 oxidation potential and a 0 reduction potential. However, as you can imagine, in practice, this is a little bit of an inconvenient cell to try and set up, because I need to start pumping 1 atmospheric hydrogen over an electrode system with 1 molar strong acid. I could do this, but this isn't going to be what I'm going to want to do every time I need to have a standard potential. So we need somebody who's a little bit more practical for actual lab settings. And that's where the silver-silver chloride electrode comes in. So the silver-silver chloride electrode has a silver chloride solid reference electrode, which can be reduced to form silver, producing a single chlorine atom. And again, this process is a reduction reaction with a single electron being placed on our silver anode, and has a reduction potential of 0.22 volts, again, versus the standard hydrogen electrode. So if I'm going to treat this as a true oxidation reaction, again, this will have a potential of negative 0.22. However, we run into a slight problem, which is the fact that as I use up my electrode, I'm going to have to worry about changing concentrations of my chloride. Now, we are fairly lucky here, is that chloride is the only aqueous species, so it's the only thing that can affect the potential of the system. But that chloride concentration can change, and the more I use the system, the less likely it is to be at a 1 molar concentration. So we need to account for the fact of I need to know the activity of the chloride. Well, here we can actually get a little bit lucky, because if I, by convention, put a potassium chloride salt at the bottom of my electrode, well, that potassium chloride is going to essentially produce a saturated system of potassium and chloride. And when I do this, this is going to fix the concentration of the chloride at about 4.6 molar chloride. And when it does, it produces a very consistent potential at about 1.97 volts. Again, versus standard hydrogen electrode, if you're treating it as an oxidation reaction, because we are generally using this as our anode, it has a potential, an oxidation potential of negative 0.197 volts. And this reference electrode is referred to as the silver-silver chloride electrode. And this tends to be, again, our real workhorse electrode with a reduction potential of 0.197 and an oxidizing potential of negative 1.197. And again, we reference this system. I have a silver electrode with silver chloride solid on top with potassium chloride solvent present elsewhere in the solution, and saturated potassium and chloride ions. And again, our good old salt bridge. However, this is going to form our general workhorse electrode. So most of the time when people are using a real electrode to make measurements, this is the one that they're talking about. However, one of the things I want to make you very aware of is that there is a older counterpart of the silver-silver chloride electrode, which you should make sure to not confuse it with, because it is an incredibly accurate reference electrode, though not used as much currently, and that is our good old friend, the saturated calomel electrode, SCE. So be very cautious that when you're talking about silver-silver chloride, you use the acronym SSCE, and when you're talking about saturated calomel electrode, it's SCE, because people occasionally mix them up. And as you may notice, they do have different potentials. However, in deference to the silver chloride electrode, the SCE electrode is much older, and it is an incredibly accurate system. And what it does is it makes use of silver chloride solid, more commonly known as calomel, which produces, which when it is reduced by by 2 electrons, will produce mercury liquid and chloride ions. And again, when it is saturated in the presence of a KCl solution, has a potential of about 0.244 volts. And again, this is a very useful reference electrode, and you'll most commonly see it when you look back in the literature. However, I do want to make note of one last reference. In this case, it's less of a reference electrode and it's more of a reference system. And that's essentially what I like to call the vacuum electron. So this is an electron purely in the vacuum, not present on a solid or an electrochemical cell. So this is a reference that's most commonly used by physicists and theorists who are occasionally taking an electron out of a saturated vacuum or ionizing an electrode to produce an electron in a vacuum. So this has a reduction potential of negative 4.44 volts. And this essentially means that in order to oxidize the system or remove an electron from the surface, this is going to take about 4.44 volts. Again, removing the electron from a standard hydrogen electrode and putting it straight into vacuum. So this is something that you would not expect to happen in reality, but it makes a good reference when doing a lot of computational calculations. And so you will see it from time to time, and it's important to note that it's there. So what we can then do is make use of these several reference conditions to go ahead and take another look at our lead oxide reduction reaction. So if I go ahead and look at the reduction potential of my lead oxide versus the standard hydrogen electrode, we have a value of about 1.69 volts. So again, this isn't exactly a very favorable, this is a fairly favorable reaction, as the lead oxide will readily consume an electron. In comparison, if I use a silver chloride electrode, this potential drops to 1.49. Again, this is because the silver chloride is a little bit more reluctant to give up an electron than the hydrogen electrode is. And similarly, the calomel electrode is a little bit less likely yet to give up an electron. However, if I compare it to the vacuum, well, it turns out that lead oxide will suck any electrons straight out of vacuum, which shouldn't be too surprising. And so again, when you're making use of an electrode potential, either in the literature or in a direct measurement, be very, very cautious of what reference cell you're using, as this will change the potentials you make use of. However, you can make use of redox potentials with any of these four references, as long as you are consistent about which reference you use. So in practice, once I have my reduction potential that I care about, I can essentially use this to determine any other type of reduction potential or an overall reaction potential, simply through applying a lot of our applications of Gibbs free energy. Because what we can do is say, imagine a reaction such as the reduction of ferric iron, or Fe3 plus, to iron to solid metallic iron, and it turns out that this reaction has a fairly low potential of negative 0.04 volts. In other words, this reaction doesn't want to occur too readily. And what we can then do is make use of our convert this to our standard state Gibbs free energy of about 0.12 electron volts. Now, one of the reasons why I like making use of electron volts in this case is simply put that you can turn volts to electron volts simply by multiplying by the number of electrons present. In this case, since I've got 3 electrons, negative 0.04 volts now becomes positive 0.12 electron volts, which is a fairly useful strategy when you want a little bit more direct comparison in between voltages and energies. So we can do a similar reaction for the reduction of bleach. So bleach, or hypochlorite, can essentially combine with water and 2 electrons to form a chloride ion and some hydroxide. And again, under standard state basic conditions, so this does include 1 molar hydroxide. This has a standard state potential of 0.9 volts, which, since it's transferring 2 electrons, corresponds to negative 1.8 eV. And again, remembering that a positive potential indicates favorability, while a negative Gibbs free energy also indicates favorability. And then again, we're just counting for the number of electrons per mole of reaction. So what we can then do is figure out how to combine these two reactions. Well, in order to do that, I'm first going to need to make sure that both systems are transferring the same number of electrons. So my iron system, uh, so with 3 electrons uh, being required to reduce my iron and 2 electrons to reduce my bleach, I need to find the least common multiplier, which in this case is 6. So when in doubt, a good option is just trying to multiply the two numbers by each other, and that will always work, and you can see if there's some uh, lower shared multiplier present. So when I do this, we find that the uh, reduction potential of the ferric iron remains at negative 0.04 volts. And the reason why here actually is fairly straightforward. Volts is how much energy there is per unit charge. Well, if the amount of charge changes, that doesn't change the amount of energy per that charge. And again, one of the good ways to think about this is the energy per electron. So my potential remains unchanged as I change the reaction. My Gibbs free energy, however, does undergo a significant change because this is the total size extensive energy per mole of reaction. And as I now go from 1 mole to 2 moles of reaction, this changes the free energy of reaction. Another good way of looking at it is I change the number of electrons. So now instead of multiplying my system by 3 electrons, I now have to multiply it by 6. So I go from a Gibbs free energy reaction of 0.12 volts to 0.24 volts, or 0.04 times 6. And again, remembering to flip the signs. We do a very similar thing with my chlorate. I multiplied this reaction by 3. Potential remains unchanged, but my Gibbs free energy also becomes multiplied by 3. So this is going to help allow me combine these two reactions, as now we'll notice that all of the electrons will essentially cancel out. Now I have to consider which way would I expect this reaction to combine. So if I let this reaction proceed naturally, I'm going to want the method that gives me a Gibbs free energy of reaction that is negative or favorable. So I'm going to flip the reaction with the lower potential. So in this case, this iron reaction is relatively less favorable as it has a more negative potential or a more positive Gibbs free energy. So I can then go ahead and flip this reaction and then combine these two reactions like I always would for a Gibbs of reaction. So this means I can then go ahead and simply add together my potentials to give me a value of 0.94, and again, add together my Gibbs free energies of reactions to give me a value of negative 5.64. This is the general idea that we're looking at when we're trying to combine two half reactions together to make one net reaction. However, one of the things I want to make you aware of is that when I'm combining my half reactions, combining my oxidation and reduction reactions is going to give the same exact result as adding together my free energies. However, one of the alternative methods that we often teach in, say, a general chemistry course is simply that you can take the more favorable reaction and then subtract out the less favorable reaction. Because subtracting out, again, the reaction that the oxidizing reaction is going to be the same thing as flipping the reaction and then adding it. So again, here we're making use of subtraction is the same thing as adding a negative, and both will give you the same net reaction and the same potentials. So either way that you feel the most comfortable with is a good way to proceed. But I do want to make sure that you do not try and mix and match these methods. If you flip the signs of your reaction, you are only going to do addition. If you're going to do subtraction, leave the signs of your potentials alone. As long as you keep these straight, you should be good. However, this leads us with one last little nuance. So I may have a reaction that I can't just go ahead and look up in a table. So if I'm trying to generate a new reduction reaction, I have to essentially do a slightly different procedure. So let's say that I can't find the reduction of iron 3 to iron solid in a table. Most electrochemical tables actually won't contain this reaction because they assume you can do the following trick. which is the reduction of iron 3 to iron is simply these two reactions added together. So what I can do is, if I know the Gibbs free energy of reaction, again, for this reaction, I only have a single electron, so all I do is switch the signs and I get negative 0.7 eV. This reaction has two electrons, so I switch the sign as I go from potential to Gibbs, and I multiply it by 2. Then I can add my two Gibbs free energies of reactions together and get a net reaction of 0.12 eV. From there, we can then divide the whole reaction by 3 and get back my starting potential. So this can seem a little bit of a roundabout way, but when you look at the Gibbs free energies of reactions, you can really illustrate how this proceeds. However, there's a more simplified general form of how we can combine reduction reactions to get a new, more general form. So if I'm trying to combine two reduction reactions, so reaction 1 plus reaction 2 to give reaction 3. In potential space, what this corresponds as is taking the number of electrons in reaction 1 times its potential, plus the number of electrons in reaction 2 times its potential, and this equals the reduction potential of my third net reaction times its number of electrons. So in this case, what it means is that for this first reaction, where I have 1 electrons, I can get effectively the free energy by multiplying the potential times the number of electrons, plus the second reaction's Gibbs free energy, again the same way, gives me the third reaction's Gibbs free energy. And because every process would include the addition of the negative sign as I flip, I can essentially ignore it because it's consistent throughout. So adding the negative sign and then undoing it is a little bit extraneous. And so this is a good way to determine the potential of a third reaction, but it turns out this is also a good way if I know the net reaction potential and one of the individual reaction potentials. You can then rearrange this equation to solve for the third system. And you can combine the same idea of how you can combine 4, 5, or even 6 potentials to get one general net reaction. And from this and a relatively simple set of reduction potentials, you can determine most of the reduction potentials that you might possibly be interested in. And along with now knowing how to combine reduction potentials to get cell potentials, you pretty much have the basics of electrochemistry mastered. So next time, we're going to deal with the little nuance of how we can use electrochemistry to determine activity coefficients. Until then, take care.